Okay, hello everybody. Today we will be talking about different separate things, but we will continue with the string algorithms that we left last time, and then we will go to some other like sorting and etc. a little bit more. So what we were trying to do last time? Last time we calculate for each n logarithm n elements their identifier, where identifier is something for position I and 2 in the power of q.
Sorry, can you hide the OBS from screen?
Can I hide OBS? Okay, sure. Sorry. Is it better?
Yes.
Okay, good. So we try to get to calculate the separate identifiers for I and for the position I and their string that is starting at that position. Okay. How does this help us? So we already talked about like the suffix array. The suffix array is built in kind of the same manner. But we want a pretty interesting thing. We want to find an element, a pattern in the string in logarithmic time. That's a little bit crazy, and everything that is going starting from now, I have no idea how to properly implement it. I only know that if you calculate properly their complexity and do all the tricks that are there, then you can do in n logarithmic n. However, you still need squared memory, unfortunately, for what we're going to do next, because otherwise this will not work. Okay, let's start. So we will start building the suffix tree in an interesting manner. So we will start with the suffix tree of iteration 0. Oh, sorry. Here is the root, and there are n children. It has n children. So this is the string from 0 to n minus 1. This is the string, the suffix from 1 to n minus 1. This is the suffix from 2 to n minus 1, and so on and so forth. So it has their root has n children. As you could understand, this is pretty hard to store, in the sense that, okay, for example, here it is in some sense possibly even simpler to store, because you have n elements and you have will have n children. I mean, these are, if you think of, they have identifiers from their from 0 to 2 in the power, like k, where k is their size of the string, right? So like the string s is 2 in the power of k for simplicity. So here it is like the identifiers. This is identifier 0, 2 in the power of k. This is identifier 1, 2 in the power of k, and etc. Since we have 4 different, if we fix the length of the string, all identifiers will be different, right? So we start with all their different identifiers here, because these are these suffixes are different strings. However, we want to build a tree, obviously the suffix tree, that kind of joins some strings together, and we have like split positions and etc. So what we are doing here, we will take for each node here, so here is one node, we take the halves of the strings, and merge the same half of the string. So like after that, after one iteration, we will have the tree T1 that will sound like that. where this length of the string is 2 to the power of k minus 1, and here is also 2 to the power of k minus 1. How to do that approximately? For each node, we will have the list of identifiers. So this is their identifiers from 1 to n, or from 0 to n minus 1. I don't really care right now about that. And then you just take, okay, I will take their all their children there, and I take their halves. So, and in one array, you could, like in one position in the array, you could like write their new node there. You just create for each of these parts a new node and try to check which new node we take. So we just write down into an array of 1, etc. And their identify their vertex v prime, which is here. So this is the vertex v prime. So in this case, three parts has been written together at the same position, from which after that we will get the v prime. So like this is kind of in the terms of reserve commit or something like that we already discussed about. So you try to unify, like, or for how we calculate BB, we try to unify the prefix here, and by that prefix, but the identifier of that prefix, you want to get the new vertex. To do that, like we try to write the same guy to the same element, and we will get v prime out of there. I don't know, like either x1 wrote this v prime or x2 wrote this v prime. I don't care who will win. I will only need that these two elements are like these two strings are going through the v prime.
So again, we run before for every suffix and take IDs for the first half.
Yeah, in this case we run. Yeah, exactly. In this case, like how it will typically work. We will take each node in the suffix string, and then split the corresponding string into halves, and then try to join the strings together, if we can. At the beginning, we have only one node with n children. We split it to halves. And then we run the iteration so that the same prefixes we join together. So our main thing is take each node and join all the prefixes there for each node. So for example, after that, under T2 we will take the halves here. And we will get T2 like this one, something like that, and so on. Also, this could happen at the top of the tree, of course. So like this, we do the same for this node. We split into the half and merge them, and we do the same for this node. Split in the half and try to merge them together. The simplest way how to calculate, in the worst case, the total number of nodes is n logarithmic n. I think this is quite clear. And we store all these trees separately. So we store kind of separately, right? Because like no, separately. Yeah. So and to do that, unfortunately, you need n squared memory complexity, because for each node you use a special array of length n, because we never merge the identifiers kind of in the chunks. I guess you can do that using their our radix sort that works in that will be much better here, but it will be out of logarithmic span there. So the main thing that we can build these trees in n logarithmic time and some polylog span. Okay, we build these trees until, so we will have tk trees, because like the number of the size of the string is 2 to the power of k. Then we will have k trees, like, and then we are done. So we build this kind of data structure. Any ideas on how we can find the string? Like, so we are given the string s, for which we create this range of trees, very different trees with like strange notions, etc. And then you get the pattern that you want to find in the string s. I insist here that we can find the pattern p in the string s using this kind of suffix tree approach in logarithmic time. Do you have any ideas how to do that? Okay, let's wait a little bit, then I will explain, I will give next hint on how to do that. I guess, I think I forgot to tell you something specially for that. Let's think that we like run these identifiers, logarithmic time, and let us has different BB arrays through the whole time. So BB0, BB1, and BB G. So there, and here you already have of n squared logarithm and memory, which is not very good, but it is enough for us. Like if we store these BBs, we can do something on the string P. Yeah, so like this approach is totally inefficient in the terms of memory, like totally inefficient.
Probably we can split our pattern in chunks of some size. Look for identifiers of these chunks, and then try to walk the tree.
Yeah, approximately like that. Yeah, but we need to find their identifiers for the string P. How would you do that? Possibly you have some ideas.
Are these BB arrays
they are stored.
Match?
Yeah.
Like they match pairs of identifiers into the new identifier on the biggest string. Yeah.
Yeah. For each sizes of like 2 in the power of k, so like you merge.
I assume it will be too long to reproduce the iteration, the algorithm that we use to build identifiers for the tree.
No, we already built that. We already have everything. Like we already have BBs, we have already IDs and everything else. We already have.
Yeah, but to get the identifiers for our pattern, we need to find how the strings of this pattern match into identifiers. So we need to go from the smallest strings, like one char, up to according chunks.
Something like that. Similar. So yeah. So we will start like we instead of like getting the whole ID array for each of starting from each position, we will start with identifiers for the strings of substrings of length 1, then for substrings of length 2, but not intersecting, just go there, then for 4, and for here is 8. We take BB0 or BB1, I don't know exactly, and you pass them to identifiers of these characters, and then you add them together to get their identifier of these strings of length 2. Then you take two guys here, two consecutive guys there, and just like, okay, I have two guys, I will take BB2 and get their identifier of the string of length 4, and so on. Because the number of these substrings that we are interested in linear, because we don't do for each substring of length 2 in the power of q starting from each position. This is what we're doing, right? The number of these substrings that we want to know about is linear. So in linear time and some parallel logarithmic complexity, you could get all these identifiers. Okay, then the question: how we can find the string right now in this suffix trees?
We have only this string, or only this tree. We don't have any links in it, yes?
No, we have T0, T1, T2, and Tk. We have all these trees with us. So what's going on here? We try to find the pattern here or somewhere else, right? So what you're doing, you just, if the string is bigger than 2 in the power of k minus 1, then we will go to the first tree, find the first, the identifier of the prefix of length 2 in the power k minus 1, and then go recursively from v prime. And this v prime goes recursively here, so that's, we kind of store their vertices that are not changing through time. Like if we already have this node v prime, it will be over all next trees. There. Okay, so we took like the first 2 in the power of k minus 1, and then we just go recursively for v prime and consider the next parts of the string. If the length of the string is not higher than 2 in the power k minus 1, we do some merging and we take the corresponding tree where the height of the string p is bigger than the corresponding part. So this is for t 2 in the power of k minus 1 corresponds. This is for 2 in the power of k minus 2, and etc. So, and since we're doing this in constant time, each time we go down by 2 some power of 2, and yeah, and that's it. We just go by the power of 2's, and given this logarithmic trace, we can find whether each node, whether the string is in S, like by using logarithmic n steps, where for each step we take in constant time.
Okay, but these trees are suffix trees. So what if our pattern is somewhere in the beginning and not in the like end of the text? I don't quite understand.
Okay. So suppose like there is pattern appears somewhere at the second identifier, right? So like it starts with the second character.
Yes.
So this means that it will correspond to this suffix, because like this suffix is from 2 to n minus 1. It will correspond to this suffix. What we're doing in the first case, we like kind of take the halves of the string and merge them together. So if the string is already large, like if it has height 2 in the power k minus 1, we just go to the corresponding child and we're done.
So we go. So in the root we have like child 0, and in the leaves we have the end of these suffixes. Yes.
Yeah. So these are still the starts of the suffixes. This is the prefix of the suffix.
Okay.
So this is kind of how you look for the suffix in the suffix tree of the standard suffix tree, but like with additional twist that you can do this in logarithmic time faster if we maintain all the necessary values in memory. Okay. Any questions up to now?
Okay. I think no.
Okay. Now we will consider how to implement suffix array in polylogarithmic time, and at the same time in linear time complexity as the work. So like, that's not, I guess, I'm not sure whether like, on the algorithms and data structures you were told about that. I think not. How to make suffix array in linear time. It appears very suddenly that that algorithm is very good for parallelization. It's not really complicated. So let's start. We will build suffix array recursively. So suppose we are given a string, kind of string, where each element is from 0 to n minus 1. Where their number of elements is n. And we want to build suffix array based on this integer. So like this is a little bit different rather than suffix array, because in the suffix array you're given characters. But here I think I've given like that each element does not exceed their size of an array. What I'm doing next, I will take each like I will take each three symbols that are going like at some position. I will take only three cells that are consecutive. So we will have be 0. So we have x0, x1, x2, x3, and so on. So we take, like these are, let it be not x, let it be triples, right? So this is T2, T3, and so on. So this T1 is correspondingly x1, x2, x3. T3 is x2, x3, x4. T3 is x3, x4, x5, and so on. So we, at each position, we are trying to get the strings of the substrings of length 3. Since they are not very large, so like each one consists only of 3 integers of size bigger than n, we will sort them using radix sort. We will sort them using radix sort, and then we will get some identifier from 0 to n here. So this will be V0, V1, V2, V3. So we get new identifiers for each triple. For each triple of consecutive symbols, we sort them and give them identifiers. And then we consider an interesting string that looks the following. So it is V0, oh sorry, not V0, V1, V4, V7, V10, and so on. So here, all the V's that are of type 3k plus 1. And here we'll have V2, V5, V8, and so on. And here the V's V3k plus 2. So we will split triples onto 3 parts. The triples that start at everything that is divisible by 3. The triples that has their 1 modulo 3. And the triples that started at positions that are 2 modulo 3. Okay, of course we will add here some special symbols, because otherwise I'm not sure that this will work. And then we run suffix array on this string. You run suffix array on the string, and then by that, if you do that, you will get the suffix array, like all the sorted suffixes, which positions are either 1 or 2 modulo 3. So we will get a suffix array here. Yeah.
We run suffix array on all this array or on separate chunks?
On the whole array. On the whole array. Yeah.
And we don't have identifiers that are divisible by 3.
Not like that. Not the identifiers are not divisible by 3, but their position in the starting array is not divisible by 3. Yeah.
Okay.
So when you do suffix array, you can understand that the suffix array of these parts will give us the suffix array, but only for suffixes that are starting at 3k plus 1 or 3k plus 2. So we will have, I don't know, like here, V7, v2, v5. Oh, sorry, like we're trying to write in indices here. So it will be 7, 5, 2, 4, and so on. So the suffix array gives us their identifiers of the suffixes that are only not divisible by 1 and 2.
These identifiers are taken from the original identifiers?
Yeah, from the original. So like v7 corresponds to the 7 here.
Okay.
So this means that their 7th suffix was the smallest one. This means that the next is the 5th suffix, and so on. As you can think, we can do the same, but only for we can do the same, not the same trick, but we can do the suffix array for the suffixes that are divisible by 3. So it's 3, 9, 0, 6, and so on. How to do that? That's quite tricky. Each suffix of the size of modulo 0, each suffix, it has the corresponding way to write. So it is x3k with x3k plus 1 to the end. We know the identifiers of these guys, like their position in suffix array, which will be from 0 to n minus 1. I get from here. This position I will get from here. And then to get, to sort their suffixes that starts at divisible by 3 position, we can show that it is equal to the character at position 3k on the corresponding, and some value of 0 and minus 1 that is given from the sort of all their suffixes that starts with positions 1. Then we can sort these pairs. So this will be the pair, the character, and their position of the suffix 3k plus 1 in this array, and thus we can sort their suffixes the 0 suffixes. These 2 arrays are sorted. If you think about this, these 2 arrays are sorted, and we can try to merge these arrays together as the standard merge operation in polylogarithm complexity, span, and linear time work. Linear work. Okay. The only question here is how we can compare zeros with ones and twos.
One question. You say that these arrays are sorted. You mean sorted in terms of corresponding substrings?
Yeah, in terms of the corresponding suffixes. Yes. So it is sorted in terms of the suffixes of 1 or 2, and these ones are sorted in the terms of suffixes zeros. That. How we can compare them? That's an interesting question, though. So suppose we're trying to compare their suffix 3k with 3p and the suffix from the right part, which is 3q plus 1. Luckily, we can compare in constant time. 3p is x3p, is the pair of x3p, and the suffix that starts with 3p plus 1. And this guy is x3q plus 1, and the suffix with 3q plus 2. We know the comparison between 3p plus 1 and 3q plus 2, because like we know here all their positions of the suffixes that are 1s or 2s. So we know their values here. So it's again compared to pairs. It's a little bit more complicated with 3q plus 2. It's a little bit more complicated. Instead of that, we have two characters and the string. So we have x3p plus 1, and the suffix 3p plus 2. And here we have x3q plus 2, x3q plus 3, and x3q plus 4 again. We will compare them as triples. So it is 3p plus 1 with 3q plus 2 and 3q plus 3. And the rest of the suffixes, this one is the suffix that gives modulo 3, 2. And this one, the suffix gives 1 modulo 2 or modulo 3. And we know that from here, again, from this suffix ring. That's it, and by that we merge zeros and ones and twos together, and we will get the suffix array at the end. This is their time complexity is linear because we will start with n, and then you get to 2n by 3, and then recursively you're going smaller and smaller parts, which are at the end will give us linear time, linear word complexity, and the span will be some n in the power of epsilon with some constant there, because we did this using the radix sort. We use radix sort here too much. Especially to sort the triples.
These were complexities for all the algorithms.
Yeah. So if you want to talk about the work here, each iteration works in linear time. So if you will see that this part without suffix array and the merge part, they work in linear time. So the only thing that we don't know is the suffix array, but we will have complexity something like that. Oh, sorry, we were talking about work 2n divided by 3 plus c times n, right? So that appears to be the linear work. Okay. Maybe questions?
Well, this original array of integers from 0 to n, is this our original string or not?
That's a good question. On each suffix array that you calculate, I'm trying to do that each elements from 0 to n minus 1, but for their starting point, for the start call, we just take a character and make it fit between 0 and n minus 1. But typically the character, like the different characters are like, I don't know, 256. So it's kind of constant, right? So like we can.
No, it's not a problem that character is greater than length of string, but what if characters are less than the length of string? Then it's no problem.
Yeah, no
okay.
problem. Yeah, we don't care. I just used that each element is not bigger than n. I just use that. You can always do this using counting sort or something like that. Additional radix sort on the characters, which gives you their complexity n. That gives you that this value is less than n. Okay.
And one more question.
Sure. Mm-hmm.
For this step from identifiers that are not divisible by 3, this suffix array, how is it built? Like recursively or what?
Recursively, yeah. So we recursively call the suffix array algorithm. Let's start from that. Okay. Are there any more questions about that? Okay, good. Okay, now we will be talking about sample sort. Which is quite good sorting. To be more precise, it has good parallelization, but it will work only using the quick sort, something like that, as the basic approach. So the sample sort is kind of their sort that shrinks the size of the arrays to smaller and then call and quick sort on that. If you calculate the complexity of sample sort more carefully, it will get you n logarithm squared, unfortunately. Or not. No, it will give you n logarithm squared, unfortunately. How? But anyways, we will operate only it only once or like twice for each of the array, so that is why it works pretty well. So their idea behind sample sort is pretty trivial. Instead of quicksort, in quicksort we take one sample to split the arrays into the parts. While here we will take square root of n, approximately square root of n samples. Okay, we take an array and then take square root of n samples and put them in a special array S, which we sort. Now we will have sort samples there. Then we will split this array into square root of n parts also. So this is square root of n, this is square root of n, and so on. This is square root of n. And we sort each of the parts, each of the small parts here. That is why it is n logarithm squared, because here you just sort all the parts, like in square root of n logarithmic n time multiplied by square root of n, you will get worse complexity here. Potentially, I think you can split on the parts of size square root of n logarithm n. I guess you can do that, and that will solve your problem with the sorting. So we sort this one, and sort this one. So we will have square root of n parts. Then we take the samples and we find where the samples correspond to this sorted array. So we take samples here, take these guys. You have their string of length square root of n, which is split into square root of n parts. So this is S1, S2, S3, as square root of n. So it splits our array into the parts. I think if like here you're not necessarily split by square root of n indeed, because typically it is square root of n times constant, but I think you can simply do their square root of n logarithm n, and it will be better. It will still not be precise complexity, but like still good. Then we want to make a very trick to this array, so that all the elements that are less than S1 are here, the length of S2 are here, S3 here, and so on. And then S square root of n. So what we have here, we just want, for each block, we want to take the parts that correspond to S1 and copy them here. This is S1, S2. So you take S1 and take it here. Then you take S2 and take it here, and so on. How to do that? So you need, for each element here, you want to know the position in this array. Any ideas how to do that?
We can run some scans.
Yeah, so that's an interesting feature. So why this sample sort is working really good? Because it works well with memory of not very large chunks that can fit into the cache. And right now we want to run scans here. So we know the sizes of these parts, and we can make their table that will calculate the size. This is S11, S12, S1 square root of n. This one is S21, S22, S2 square root of n, and so on. And so on and so forth. So these are the number of elements from the first part of the array that is less than S1, this is less than S2, and etc. And yeah, I think this is Sn plus 1. Square root of n plus 1. The problem is that we want to run scan in this direction. we want to calculate the scan of everybody that are less than S1. And here comes the problem, right? By the rows, we'll be quite fast, but by the columns, this totally ruins cache efficiency and etc. So like this, as you know, you can traverse an array. It is much better to traverse an array row by row rather than column by column, because this can give like 10x worse running time. Okay, for that we'll call a special transpose function. This transpose function will transpose this matrix. The transpose function is quite trivial. What we are doing, we take the largest size of their block, and then you tell, okay, please transpose me everything on the up and everything on the down, and call this recursively. And then like split into the halves here, then we reverse transpose them, responding already there. And by doing that, you have better cache locality here, and using this transpose function, if you do this like in the proper manner, it will have quite good cache locality. And then you will have, like using this transpose, you can calculate the scans there, and then move everybody to this array, and then you call the sort function for each of the block recursively. And that's it. So this is kind of the work of cache efficient algorithms. It appears that sample sort uses it very well, but there is like papers. I've seen at least one. I don't remember whether I saw it more than one, but like still it works good for with memory usage. And then when you go recursively very down, like, and your size of the array is 1,000, you just call std sort, and that, and like, it will be very fast, and everything should be fine. Questions about sample sorting?
One question. So when we have plotted these chunks of square root, what we do again with the samples? We find their positions or what?
In which part? Here?
Here. Yeah.
Here. Yeah.
Yes.
We just go sequentially, so we kind of do them. Here we do the merge procedure. Kind of. So this chunk is sorted, all as samples are sorted, and then you just go from left to the right sequentially. So like this part is sequential. So we just call their like kind of merge, something like that.
So we insert our samples into each of the chunks.
We don't have to insert it. We just need to find the positions, which one, like which is less than S1, which is less than S2, which is less than S3, and so on. You kind of do you kind of do this with the similar to merge function.
Okay.
Okay, any other questions about sample sort?
No.
No. Okay, nice. Mm-hmm. Okay, I have 12 more minutes. So let me try to explain you how to build convex hull in parallel. And then we will be done, like we almost done with parallel algorithms. So like I will be talking, like next week we will be talking about the scheduling, which will be the technical lecture again with mathematics, etc. So we will prove that work stealing scheduler works pretty well. And today we are finishing with algorithms. So congratulations, we're almost at the end. And then I will decide whether I will give you lectures on concurrency. So that depends whether you need this or not. I'm not sure that's you. Okay, convex hull. I will start with the standard way how you do convex hull, so that we will not have problems. So I take the leftmost guy, the rightmost guy, drew a line through that, and then we will have the guys that are on the top, the guys that are on the bottom. Then I split them into the two halves there, and run convex hull on their upper part and convex hull on the bottom part separately. This simplifies a little bit the algorithm. So right now we are considering their top part of the convex hull, and we will do this recursively. So we will split by their middle node, by the middle vertex, or point, like that's x m divided by 2. So you can sort these nodes by their x coordinate. Then I split it into two parts. I recursively call the convex hull on the left and the convex hull on the right. Then the only question is how to merge these convex hulls together in the reasonable time. I think it is quite easy to see that this thing can be done in n logarithm n if we can find the line that touches both of them. Then the convex hull will be like this part, then this guy, and this part back. And if we do this in linear time, if we can find this line in linear time, then the total complexity of the algorithm will be n logarithm n. Since it will be something like that, it will be Wn equals 2 times n over 2 plus constant n. This is n logarithm. This, if you remember from Master theorem, this is n logarithm n. I mean, this is the same as merge sort or any other divide and conquer problems. Okay, so let me draw a much larger convex hull here. And we want to know whether how to find their common, how it is named? I'm not sure that I know the proper words for that. If somebody could help me.
Name what? That line?
Yeah.
Or?
Okay, tangent. Yeah. Okay. Good. So this is the tangent. Okay. I already forgot for a long time what's happening there. Okay. So we will do a pretty interesting thing here. we will do kind of binary search. So typically you can find the common tangent in logarithm squared time using two binary searches. How to do that? We will take, we will have two binary searches which are inside each other. And their idea is pretty simple. We take the middle node here, M, which we take, and then we want to build the tangent from this point M to the right convex hull. This can be done simply because there are two types of tangents. The one that connects the guy to the left and the one that connects the guy to the right. So these are two tangents, and you can say that. So here is node, this node and this node. You can understand that their resulting tangent, like that we want to find, is somewhere here. So you can for a node here and a node there, you can understand whether your tangent is either to the left or to the right. And then you build the tangent there. So like you build the tangent here. You find the tangent. And then you can look on this part. So this is tangent again. And you can say, for this node, for this convex hull, this M is to the left or to the right for the real tangent that is going here. Because, for example, if you have tangent like that, you can see the difference, right? This tangent has on the left, kind of the convex hull on the left, while here it has on the right. So doing two binary searches inside, you can do this in logarithm squared time to get the common tangent. Like for that we need to find by that you find the common tangent in logarithm squared. Their parallel algorithm is a little bit more complicated, but it based on this approach with their tangents, where you can build a line between 2 points and can say where I should go to get the tangent, either to the left or to the right. So we will do this again as two inside binary searches, but the binary search that will be a little bit trickier. So let's consider the second binary, we have the node here, and we want to find the tangent to the right part. Okay, what we are doing there, we take all the nodes that, all the square root of nth node. So like the 0th, then square root of n, then square root of 2 square root of n, 3 square root of n, and so on. I take only these nodes. And I run, I took this node and I try to get where is the tangent here, which will be done in squared n work, but polylog complexity. Why am I doing this?
Can you say again, starting from taking each square root?
No, it seems I really don't care here, since I can calculate their common tangent in logarithm squared time. I think the main idea where that you can get better span. Yeah, I think like logarithm squared is larger span than we are trying to deal with. So like there are two binary searches will work in logarithm squared of n, and I'm right now trying to do that in logarithm n complexity of the span. So yeah, I hope this makes sense. Otherwise, you can just apply logarithm squared approach and you're done. While here we are trying to tune the span a little bit closer. So we take the right convex hull, and we take square root of n nodes, like the 0th, the square root of n, the 2 square root of n node, and so on. Okay?
Okay.
Then we can understand, like as previously, you can understand for each node where it lies in comparison to the tangent. So like here is the tangent. And for each guy, I know it is to the left or to the right to the tangent. So like this one is to the right, this one is to the right, this one is to the right, this one is already on the left.
We take this tangent from any node
From
of
this,
the hull.
we just do for one node. So we take a node P here.
It's randomly chosen, yes?
Not right. Like right now, I'm trying. The algorithm in log squared means that we do a binary search here, and then recursively binary search here, and find their tangent.
Yes.
We are doing approximately like that, but right now we have the node here is fixed, for example. So it will be also searched later. So it will be two inner sorting algorithms. But we will do this. Okay. So
I have a question. Why can't we take the highest points in the left hull and in the right hull? Probably that will be the tangent, or I'm not right.
No, that's not true, of course. I mean, you can have something strange like that here, and your tangent will be that.
It will not be the minimum, yes?
Yeah, yeah.
Okay.
It's not necessary to be the maximum, unfortunately. Yeah, I mean that's a reasonable thing to ask, but it doesn't work, unfortunately. So you can do here. You call for square root of n, and you're like, oh, I know that our tangent point of for this point P lies somewhere on the part in between where you have right and where you have left. So you know that your pair for the vertex P lies somewhere in between here. Lies somewhere here. You can see that their number is square root of n. So we again can call everything in parallel, and we will find the node for the tangent. So that's it. That's it. Like how to find the tangent from any node, any vertex of the left convex hull.
For what can we run parallel for each node in left hull?
No. Right now, given the node on the left, we can build a tangent.
Yes, but I don't understand where to apply parallelism.
I apply here because I consider all these points in parallel, all the square root of n points in parallel. Yeah, because you can answer the question where the tangent is on the left or on the right in constant time. Okay, now we know how to, given the node on the left, you can find its tangent. What we're going next? This will be kind of two inner binary searches, so they're not really binary, but for example, in comparison to the binary search, as you can see here, we did this in kind of constant time, right? Because you take you don't have the binary search there. You have how to say it? You have the you do not the binary search, which kind of the number of iterations is logarithmic n. Here the number of iterations is 2, so it is kind of better than binary search. But with the word complexity is worse, but the span complexity is better. Not really. Yeah. So like yeah, I have to talk here that we are working in CW prom. Otherwise, this indeed doesn't make sense, because if you have parallel 4 there, you will get logarithm and span complexity, and nothing will make sense, of course. Now, how to finish the algorithm? So we take, again, here, we take 0th position square root of n, 2 square root of n, and so on. And for each of these nodes, I will find the tangent of the right. So I took these nodes, and I find the tangent. That. Like something like that. And I can say for each of this guy, again, where the tangent is, it's either to the left or to the right. So for example, for this guy, the tangent is on the left, this guy is on the left, and this one is for the right. So in square root of n, you can understand on which segment you want to have your real tangent to both convex hulls. And then there is square root of n elements, so we can go again in parallel, and we find their tangent in the convex hull, for the convex hull. Yeah, and as you can see, if we consider CW prom, everything is done in constant time. That's a pretty interesting thing here, is that the binary searches, unfortunately, like if you do the binary searches on P processors, unfortunately you will get worse span in the fork join model. You will get worse span than the standard binary search. And here, and if you think about very prom, then the span of the algorithm will be less. But unfortunately, on the fork join model, you cannot improve binary search. Unfortunately. So, and why I split this into square root of n parts is that because the total running time will be linear, and we're fine with that. So for each square root of n on the left, we consider square root of n elements on the right. Thus, in total, we will get not logarithm squared binary search complexity, but linear complexity, and it does not affect the running time. Okay? If there are no questions, I think we're done with parallel algorithms. So like we will talk next week. If I will be in the good mind, we will talk about their scheduling, but I'm not 100% sure. Otherwise, we will, like, I don't know what we're going to do, to be honest. Right now, but you could say that you passed in parallel algorithms, of course, and in 2 weeks we will start, like, I guess in 2 weeks we will start by looking at the courseworks, and then we will be almost done. There are no more homeworks for there. So that's it. I will stop the stream. Thank you for coming.